Hello everyone, I once again welcome you all to MSB lecture series on transcendental chemistry. This lecture is 30th in the series. In my previous lecture I started discussion on ligands having carbon as donor atoms. Let me continue from where I had stopped. So, I showed you about the difference between Fischer carbene and Schrock carbene, and we have one more carbene called N heterocyclic carbene. And if we just look into N heterocyclic carbene, this is how a typical N heterocyclic carbene looks like, and this carbon has a lone pair very similar to carbon monoxide, and that can be given to metal through sigma bond, and then it has pi star. To pi star it can take electron density from metal through back bonding. So, it also comes under non-classical ligands along with carbon monoxide, phosphines and other olefins. I have also shown how the sigma bonding happens here. Sigma bond you can see here, and then the back bonding again pi star is there, and if you can see when we have this pi star on carbon, there is a competition for electron donation from both metal as well as nitrogen, which has a lone pair. As a result, what happens, it is always very easy to take electron density within the molecule rather than taking from metal. As a result, what happens, it has less inclination to take electrons from metal through back bonding. As a result, what happens, it is a good sigma donor, but relatively weak pi acceptor compared to carbon monoxide or tertiary phosphines. For the same reason, it has, of course, this kind of lone pair of nitrogen coming to carbon pi star is also called negative hyperconjugation, and that is more pronounced in case of phosphorus nitrogen bonds. And also one way, the back bonding from metal to phosphorus sigma star orbitals is also called as negative hyperconjugation. That means this N heterocyclic carbenes as carbon donors can mimic similar type of chemistry we come across with carbon monoxide and olefin chemistry and also phosphines, and also they are as good as phosphines in some organic transformations as catalysts. And then of course, in metal alkoxy carbene interaction very similar, this carbon lone pair goes to the metal through sigma bonding, and once again here also metal gives electrons to pi star of carbon through back donation, and once again here oxygen lone pair also competes for this one. As a result, these alkoxy carbenes and N heterocyclic carbenes are relatively poor pi acceptors compared to carbon monoxide and phosphines. I hope it is clear now. Through orbitals also I have shown how they interact while doing back bonding or in sigma bonding. So, this is called fullerene, and fullerene, if you consider one side or one single double bond, one isolated, these double bonds can behave as isolated double bonds we come across in olefin. That means whatever the reactions we perform on olefin such as ethylene, similar reactions can be performed here. Let me show a couple of reactions here. So, let us consider when isolated double bond something like this, and this whole moiety I should call it as C60. So, if I am considering one of these double bond, there is no harm in writing something like this. In this way you can represent, and then let me treat this one with lithiated alkyne such as Me3 Si and then followed by adding acid. So, it can one can make compound like this. In a similar way, in another reaction, if I take lithium in liquid ammonia, using and later add tertiary butanol, it can form NH2. So, amination reaction can also be performed. So, that means fullerene can also be considered as a simple organic molecule, and one can perform reactions I have shown here or several other similar reactions. Another reaction I have shown here, you take this fullerene C60 and treat with Grignard reagents such as phenyl magnesium bromide in presence of this cuprous bromide complex having dimethyl sulfide, and you take this one in toluene and THF mixture at -78 degrees centigrade, and once the addition has to be done at -78 and then it should be warmed to room temperature, and then excess of this one can be quenched using ammonium chloride, aqueous ammonium chloride, that leads to the formation of something like this. You can recall now it resembles C5H6 cyclopentadiene, and when you add metal alkoxide to it, I have given metal alkoxides of one of these things here in THF, and you can make it eta 5, and you can see a half sandwich compounds coming something like this. So, that means one of the 5 membered ring can also be utilized as a eta 5 ligand from C60. This was reported in 1996. If you want more information, you can refer to this journal here. So, now look into another important ligand among carbon donor ligands, that is cyanide ion, can form complexes with transition metal ions in aqueous medium and also with group 12 ions. Group 12 ions means zinc, cadmium and mercury. They have completely filled electronic configuration, that means Nd10, N plus 1, S2. Nevertheless, it can also form complexes with these metal ions also. Due to negative charge, cyanide ion is a poor pi acceptor. That means due to the negative charge, cyanide ion is a poor pi acceptor, but forms complexes with metals in both low and high oxy states. Due to large nephylaxetic effect, it occupies higher position in spectrochemical series. So, otherwise it should have been much lower. We come across something called as nephylaxetic effect. Because of this one, it occupies higher position in spectrochemical series. I have given two very important complexes here. You can see here nickel is in 0 valent state, tetracyanonickelate, and counter cations I have shown as potassium. This is one example of cyanides stabilizing metal in low valent state, and of course we have another one here stabilizing iron in +3 state, hexacyanoferrate. I shall elaborate more about nephylaxetic effect and also how this is related to Raka parameters when I talk about electronic spectroscopy. Nevertheless, I should tell you little bit about nephylaxetic effect before I proceed. So, when an atom has more than one electron, there will be some electrostatic repulsion between those electrons. You should remember that the amount of repulsion varies from atom to atom depending upon the number and spin of the electrons and the orbitals they occupy. So, Raka parameters were generated as a means to describe the effect of electron-electron repulsion within the metal complexes arising due to the formation of metal to ligand bond. The Raka parameters are A, B and C. In the case of Tanube-Sugano diagrams, each electron configuration split has an energy that can be related by the B value, and also one can also use Orgel diagram to predict and calculate Raka parameters for various electronic configurations. The decrease in the Raka parameter B, as I mentioned A, B, C are there, and the decrease in the Raka parameter B indicates that in a complex there is less repulsion between the two electrons in a given doubly occupied metal d orbital, that means in EG, then there is in the respective Mn plus gaseous metal ion before it enters into ligand field. So, which in turn implies that the size of the orbital is larger in the complex. So, this electron cloud expansion effect may occur for one or both of two reasons. That means this expansion of electron count can be attributed to two important reasons. One of the two reasons is that the effective positive charge on the metal has decreased because more and more electron density is coming from ligands through sigma donation. Since the positive charge of the metal is reduced by any negative charge on the ligand, the d orbital can expand slightly. You should remember, I tell you again, since the positive charge of the metal is reduced by any negative charge on the ligand, especially anionic ligands are approaching the metal, the orbitals can expand slightly. So, the overlapping with ligand orbitals and forming covalent bonds increases orbital size, because the resulting molecular orbital is formed from 2 atomic orbitals. So, the reduction of B from its free ion value is normally reported in terms of nephelauxetic parameter that we see in case of cyanide ligands. That is, the parameter beta is nothing but the ratio of the B value of complex to the B value of free ion. Experimentally, it is observed that the size of the nephelauxetic parameter always follows a certain trend with respect to the nature of the ligand present. So, I think you should remember to this extent about nephelauxetic effect and how Raka parameters are related to this one. When I discuss about electronic spectroscopy, I shall show you how to calculate by taking 1 or 2 examples. So, this one is Prussian blue. Actually, when you see textbook, they show simple K4Fe CN6 or something like that. Actually, this has 3 Fe2 ions and 4 Fe3 ions, and Fe2 ions are surrounded by 6 cyanides in this fashion, and then these are surrounded by N binding in this fashion. So, this has a complex structure. If you are curious, this is how the structure looks like. You can see here iron, the middle iron in +3 state are coordinated from 6 directions having octahedral geometry in this fashion, and this continues in 3-dimensional form. So, this is how it looks like. For clarity, you can see the labeled atoms with the different color, that should tell you how the arrangement is made for these Fe3 plus and Fe2 plus in the lattice. So, cyanide is one of the very important ligand in coordination chemistry. Let us look into the coordinating modes of cyanide ion. The simplest one is a terminal in this fashion, and you should remember we have a lone pair on nitrogen. So, it can also form bridging or dimetallic complexes through both carbon and nitrogen bond, something like this, and also this triple bond can also coordinate to metal in this fashion, or the carbon itself can bind to 2 metal centers, very similar to carbon monoxide. Okay, bridging can be this type, and you should remember that still we are left with a pair of electrons here. So, third metal can come and coordinate to N in this fashion, or if its bond is reduced, it can have a bent structure, something like this, where both carbon and nitrogen are making bond with the 2 same or different metals. It can be homo or hetero bimetallic complex. So, these are some of the important coordinating modes of cyanide ion. Then how to characterize cyano complexes to confirm that we have cyanide and it has a particular type of coordination mode, that comes from analytical and spectroscopic data. The important one is IR. So, IR shows a sharp intense band between 2000 to 2200 centimeter minus. Due to nitrogen lone pair, it can act as a bridging ligand with MCN links, that is what I mentioned. So, such complexes are polymeric in nature with chain structures. One such example I showed you, that one is Prussian blue, and gold cyanide, zinc cyanide and cadmium cyanide all show chain structures. One such silver complex was also prepared in my group, and that I showed you. I will show you in next slide. And for example, here you can see when zirconocene diiodide, this is called zirconocene diiodide, it is treated with hexacyanoplatinate, forms a heterodimetallic complex of this type. It has a polymeric structure. You can see here, this is called cyclodiphosphazane. It is a inorganic heterocyclic ring having alternate phosphorus and nitrogen, having 4 membered, and it is planar, and phosphorus has a pair of electrons. Now, this one has a cis conformation, and this acts as a wonderful ligand system, and we have explored its rich coordination chemistry and organometallic chemistry, and also its utility in various applications. So, one such ligand I have shown here. So, when this ligand, a bridging bidentate ligand, is treated with silver cyanide in astronitrile, it forms one dimensional chain of this fashion. You can see here silver is tetra coordinated, having a tetrahedral geometry, and 2 phosphorus from 2 different N2P2 rings are binding here, and 1 nitrogen of cyanide is binding here, and this one is cationic and this fragment is anionic because 2 cyanides are there. So, that means it is a charge balance is there. This is anion, this is a cation, and here one is 4 coordinated, one is 2 coordinated, and it grows to have something like this zigzag one dimensional polymeric structure it has. So, this is how the X-ray structure depicts for this molecule. Another interesting compound is there, you can see here where cyanide acting as terminal as well as a bridging ligand. For example, you see here KFeCrCN6, the green isomer, that means it exists in 2 isomeric forms. Green isomer has iron 2 and cyanide through and chromium 3 binding to N, whereas in case of red isomer opposite is true, chromium 2 binds to carbon and then iron 3 binds to nitrogen linkages. One such isomer I have shown here. Of course, you should be able to tell which isomer it is, whether it is green isomer or red isomer. From this data, from this information you should be able to tell. And here M can be a main group element as well, for example silicon, germanium or tin can also be used here, and other metals such as chromium 3, manganese 2 or iron 2. So, all this, that means you can make a series of complexes of this type here. And if you again want more information, very useful information is there if you read Advanced Inorganic Chemistry 6th edition, and this information is there around this page. So, now let us look into other carbon donor ligands. The important ones are carbon dioxide from the point of reduction of carbon dioxide. Lot of groups show enormous interest and make lot of complexes eventually to reduce carbon dioxide. It is not very easy, nevertheless people have succeeded partially in converting that into useful organic molecules. And then let us also look into carbon disulfide and also carbon oxysulfide as ligands. So, these 3 are belongs to cumulines category, and these 3 cumulines react in a similar fashion with appropriate metal reagents to form complexes. That is the reason I have put all these 3 together, and more emphasis is given to the chemistry of carbon dioxide with an aim to use it in organic synthesis to convert into useful organic chemicals. Now, let us look into all possible coordination modes of CO2, and this is very important, you should remember. So, when you want to activate carbon dioxide or when you want to reduce carbon dioxide and when it approaches a metal and how it interacts, one can see here, and it can also bind in eta 1 fashion simply in this way, or it can also bind in eta 2 fashion. Initially breakage of one of the double bonds is very essential, and it has to be polarized, and then it can be added in a concerted fashion like this, or it can also bridge 2 metal centers in eta 2 fashion in this way after breaking one of the CO bond, or it can also be eta 2 mu 2 and eta 3, because this one is eta 3 because the hapticity is 3 here, but here it is bridging as well as chelating. One can also see class 2 type where oxygen lone pair is coming in this fashion, and also one can also see another type of mu 3 eta 3, but all going to different metals, or one can also have mu 3 eta 4, or one can have mu 4 eta 4, that means bridging 4 metal ions, mu 3 means bridging 3 metal ions, mu 2 is bridging 2 metal ions, and here also it is bridging or linking 4 metal ions here, but it shows eta 5 coordination because here eta 2, eta 1, eta 1, eta 1, so eta 5. Interestingly, examples are there for each case. We may have plenty of examples in some cases, but we have few examples in some other cases. Let me show a couple of examples here how one can initiate the binding of carbon monoxide to appropriate metal complexes. Here this is a rhodium diarsine chloro complex, rhodium 1 complex, and again this arsine diarsine is a neutral ligand very similar to diphosphorus, and for simplicity I have omitted A substituents, they should be PPH2, they should be PH2 here. Initially it has something like this kind of structure here, square pyramidal structure, and then CO2 comes on the 6th position and then it forms a complex like this. And also you can see here how concerted addition happens when you take this carbon monoxide and add oxygen. It appears like insertion of oxygen takes place here, and it appears as if we have inserted carbon monoxide in an oxidative addition fashion. So, this is some sort of generating CO2 through by some other means, not directly taking carbon dioxide, but taking CO is there and we have taken this one and it forms a complex. Okay. Other examples are there, you can see here. This one has a carbon dioxide bound complex. For example, you take this one and treat with Wittig reagent, and that means whatever the Wittig reagent does for a ketone, same thing can also be done onto a carbon monoxide CO double bond on a metal center. So, that means you can see something like this happening. Of course, once this goes off, this oxygen is abstracted to come here as trimethyl phosphine oxide. And one can also generate CO2 using two appropriately substituted metal reagents. For example, here one have a hydroxyl group we have, in another one we have carboxylic group here. So, if you take these two, elimination of water takes place. So, here elimination of water, condensation takes place to have a bridging CO2. That means we came across few examples of coordination modes I showed you here, and you can get an example for all type of coordination modes if you look into textbooks, especially 6th edition of Advanced Inorganic Chemistry by Cotton and others. You take this anionic homoleptic tetracarbonyl ruthenium complex and treat with carbon dioxide, you can generate something like this, and then CO and CO3 2- comes out. That means here it acts as a source of carbon monoxide here. Few examples I have shown here very similar to what I showed in case of MH, but it's slightly different to what are the different bonds CO2 can be added. I have shown here. For example, you take MH bond and if you can add CO2 or you can insert CO2 either in this fashion or in this fashion. So, that means I am giving you more avenues to use CO2 or activate CO2 molecule in your own metal complexes. Yeah, so, for example, if you have MH bond, still that can be used for reducing carbon dioxide, and if you have MOH bond, still you can use it. Of course, you have to choose the right kind of ligands here for performing this reaction with better yield and better conversions. And then you can also insert carbon dioxide between metal to carbon bond in this fashion, or it can also form something like this. Or if you take a metal to amide bond, you can insert this one in this fashion, or if you take simply a oxo bridge metal complex, you can insert CO2 in this fashion. So, these are all wide variety of reactions, that means there is plenty of scope to activate CO2 depending upon what kind of other ligands we have on metal and what is its oxidation state and how this can facilitate the activation of CO2. One should look into it thoroughly, then performing some reactions would be very easy. Let me stop here and continue discussing more about carbon donor ligands in my next lecture. Until then, try to look into more details about carbon dioxide and its complexes in standard textbooks.